So the first question that I received from a student, very interesting question. It deals with homework problem number 3. And this is what I encourage you guys to do. Problem number 3 was actually the SLD shown over here, and it has multiple generators and a transformer, and the fault is happening on the secondary of the transformer. The student had no issue solving the actual problem. The student followed up with me and said that what will happen if a symmetrical fault happens on the generator bus instead of the secondary of the transformer in homework problem number 3? My understanding is that since there is only one source, transformer impedance will not be involved in the fault current calculation. According to the original problem statement, this is how it looks like, right guys? You guys remember seeing this problem in the homework assignment? Yeah. So what the student is saying that, let me assume that the fault is actually happening over here. If that is the case, then the student's understanding is that the transformer impedance will not be involved in the fault current calculation. Do you guys agree or disagree with this? Exactly. So that is correct. Unless there is also a source downstream over here. So if we had some other sets of generators or even big rotating machines, okay, and even induction machines, large induction motors, there would be contribution from here to here. But the transformer as it is, we know that the transformer is not a source of fault current contribution. In our sequence diagrams, the transformer's impedance is gonna show up simply as an impedance. Nothing more, nothing less. Correct? So I encourage you to look at these problems in a way that can help you understand the concept 360 degrees. Because this level of anticipation and proactive learning, should I call it, if I can call it that, will help you develop a very well-rounded understanding of the concepts. Does it make sense, guys? So here was my response. The way that we approach these type of problems, we should start by identifying the sources of fault current contribution. So as far as the sources of fault current contribution are concerned, we have G1, G2, G3, the 3 generators. They directly contribute to the fault current. The fault current calculations will involve the subtransient reactance of these generators. Now, those of you who've gone through this problem in detail, one of the first steps that we had to do was to recognize that these generators G1, G2, and G3, they were all on different MVA bases. Remember, guys? And what did we have to do? We had to convert them to a common base. So there was a base change formula involved. And I've mentioned this several times before as well, that by the time you get to section number 4 and even section number 3, a lot of basic power system analysis techniques and tools will be considered prerequisites. 3-phase system analysis, per unit systems, sequence components. Correct? So per unit system base change formula may be considered as a standalone question in section number 2, but it would just be a line item when you're solving fault analysis problems. Clear? So when you go about solving this problem as we did, we had to bring them to a common base, but we're not going through the numerical exercise over here. I'm just addressing the question that the student had. So identify what are the sources of fault current contribution. And there are 3 sources of fault current contribution, G1, G2, and G3. There's nothing shown on the downstream, so don't read into it. What is the role of the transformer? If the fault is strictly on the generator bus, right here, right? If this is the fault location before the transformer, so on the primary side of the transformer, the impedance of the transformer does not play a role in the fault current calculation for that specific bus. The transformer's impedance would affect calculations involving faults downstream, for example, the secondary side of the distribution system, as shown in the original question. But for the concern that the student has, that if we are having a fault on the primary of the transformer, which is the generator bus, then it will not come into play. And remember that for a symmetrical three-phase fault, the equation is pretty simple. Pre-fault voltage divided by the total impedance. In this case, the impedance would be that of the generators, and the generator total impedance would be the parallel of the synchronous reactance of G1, G2, and G3. Okay. And in order to calculate this G1, G2, G3, notice that I'm indicating that this is new because we have to bring them to a common base. All right. Does it make sense? So very interesting question, very thoughtful question that was asked by the student related to problem number 3, but essentially created a new question out of this problem. And this is a systematic way of approaching this. What common bus should we bring them? What common base should we bring them to? I know it doesn't matter, but would 30 be easiest? Yeah, so that's a good question. In terms of bringing these generators to a common base, I think I've discussed a stepwise methodical approach in terms of identifying a common MVA base, both in the context of the per unit system analysis as well as fault analysis. The starting point ideally should be the problem statement. If the problem statement tells you specifically that we are going to use overall system base value as this particular kVA or MVA, that is what you're going to use. Okay. The second option would be to use the highest MVA base, as Naz is saying, right? So when I look at the entire system, so Chris, your point is right. I mean, 30 MVA is the highest amongst the generator. But if you look at the highest overall, that is 60 MVA. So the highest for the overall system is going to be 60 MVA. And there's nothing right or wrong with these. You can use any MVA base. Your per unit values are going to be different. The actual values are always going to be the same if you carry out the per unit system analysis properly. Okay. Now, I wouldn't go with 100 MVA in this case because it will save me one calculation. So let's say if I keep 60 MVA as a system base, then I'll have to come up with a new value for G1, a new value for G2, a new value for G3 using the base change formula. And the 60 MVA obviously is going to remain as it is, correct? But if I was to use 100 MVA base, then I'd have to change all of them. In that scenario, maybe using 30 MVA would be a better choice for the same reason. At least I wouldn't have to come up with a new one for this one, right? 100 MVA means that I'll have to change all of them. 60 or 30 would mean that I will have to change at only 3. So it's sort of a judgment call. But again, there's no right or wrong answer because the base change definitely is going to impact your per unit values, but the base change does not impact the actual values. So if the answer is asking for actual values like fault current values, like impedance values, and so on, then they don't necessarily have to provide you information about the base. Please listen to this carefully. I think I mentioned this in per unit as well. So if the question is silent about base recommendation, they cannot test you on per unit values. Like options A, B, C, and D cannot be per unit quantities. Because for them to sort of test you on per unit, they have to fix base values. But if they are silent, okay, they don't provide any base values, okay, floating base values, let's say, or discretionary base values, then A, B, and C, D have to be actual values, amps. Because regardless of the base that you select, the actual values remain unchanged. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, StudyforFE.com.